Hello, it's Stat 134, Lecture 31. Last time we did independent normal variables, section 5.3. So we saw that for t exponential 1/2, the Rayleigh random variable is defined as the square root of t, and that it has density r e to the minus 1/2 r squared, r positive. Also, using the Rayleigh distribution, we showed that if z1 and z2 are IID standard normals, then the sum of squares of z1 and z2 is an exponential 1/2. And furthermore, the density of the standard normal has constant 1 over the square root of 2 pi. The expectation of z is 0 and the standard deviation of z is 1. We defined a normal random variable with mean mu and sigma squared as a change of scale of a standard normal. So if we let x be mu plus sigma z, using the change of variable formula and knowledge of what the density of the standard normal is, you get the density of a normal mu sigma squared. Finally, we showed using moment generating functions that if x1 and x2 are normals with different means and variances, then a linear combination of x1 and x2 is normal with mean and variance as shown. So today we're going to do another example about linear combinations of independent normals, and we'll introduce the chi-square distribution and convolution formula for the density of a sum of random variables. So we start with a concept test. So if x is standard normal and y is standard normal independent, the probability that x is greater than 2y was in fact 1 minus the CDF of 0. And the idea is to write x greater than 2y as x minus 2y greater than 0, and x minus 2y is normal with mean 0 and variance 5. So we can normalize and get the probability of z is greater than 0 is 1 minus phi of 0, or a half. The second problem is really quite analogous, and the answer is A. Here again, we write that the difference of x and y is normal with mean 2 and variance 13. The rest is the same. So the chi-square distribution. So we start off with the fact that if z is standard normal, then z squared is a gamma 1/2 1/2. This is shown at the end of the notes using the change of variable rule. So let's recall that if t is gamma r lambda, then the moment generating function for t is lambda over lambda minus t to the rth power for t less than lambda. And so the moment generating function for z squared, since z squared is gamma 1/2 1/2, would be 1/2 over 1/2 minus t to the 1/2. And so for z1 to zn IID standard normals, the moment generating function of the sum of squares will be the product of those n moment generating functions. So the exponent now for the moment generating function is n over 2. And by the uniqueness of moment generating functions, we conclude that the sum of squares is a gamma n over 2 1/2. The sum of squares of standard normals of independent standard normals is called the chi-square distribution with n degrees of freedom. So, for example, if we only have 2 independent standard normals, we showed that the sum of squares is a Rayleigh squared, and we also showed that a Rayleigh squared is gamma 1 1/2. Finally, we did the density convolution formula. So we'll start for the discrete case. In the discrete case, so let's say that we have x and y are non-negative random variables. So we have uniform, say 0, 1, 2, 3, 4, 5, 6, x and y, and let s be the sum. So we want to find the probability mass function for s. So the probability that s is 3, for example, if s is 3, then x can be 0, 1, 2, or 3, and y would then be 3 minus 0, 3 minus 1, 3 minus 2, 3 minus 3. So we get the convolution formula, summing over all the different values of x from 0 to s, and we have the joint function here where y is written in terms of s and x, because y is s minus x. So for the continuous case, we have x greater than 0 and y greater than 0 continuous random variables, and we're going to find the density of s. So now s is x plus y, or y is s minus x, and you can think of the equation of a line having slope minus 1 and y-intercept s. So probability that s is in ds would be the shaded green region here, actually the volume under the joint density over this green region, and the probability that s is in ds, x is in dx, is the volume under the joint density over the green region shown in this picture here. And so notice that if little x is on the x-axis, then the corresponding point is s minus x, because that's what y is for that given x. So we can approximate the volume as the height of the joint density at x, s minus x, times the area of the green region here. And so x now runs from 0 to s, because x has to be less than s, as you can see here in the picture. So the probability that s is in ds then is the integral. We're going to add up all these little green parallel pipets as x runs from 0 to s. So we get the integral of x equals 0 to x equals s, probability that s is in ds, x is in dx, and so, as I said, probability that s is in ds, x is in dx can be approximated as fx s minus x times dx ds, which now we can recognize the density part of s is just that integral from x equals 0 to x equals s, f x s minus x dx. And this is the convolution formula for densities. So as an example, x and y IID exponential, and s equals x plus y, then the density, using the convolution formula, we can now use independence to split the joint density, and then apply the formula for the density of the exponential, and perform the integration, and you get lambda squared e to the minus lambda ss, and you recognize that e to the minus lambda s times s is the variable part of a gamma 2 lambda. So s is gamma 2 lambda. Furthermore, if x is a 7th order statistic and y is the 9th order statistic for a 10 IID standard uniform, we saw before the joint density is 10 choose 6 1 1 1 x to the 6 y minus x 1 minus y, and so you can ask yourself, for fixed z, what's the smallest and largest value of x? And so so z is y minus x, so x is y minus z, and so z is fixed. Y can be anything from 0 to 1, right? So now x must be between 0 and 1. So the smallest is, I'll say here, so let y be z. If you let y be z, then that would result in the smallest possible x value, which is 0, and the largest would be, we'll let y be 1. So now, as someone remarked, because x is actually the 7th order statistic, x can't technically be 0, but smallest in the sense of a limit. So there actually is no smallest, but in sense of a limit, 0 is the smallest. It's the limit of smallests, I suppose. So the convolution formula then for z equals y minus x is going to be what's shown here. So we're going to take the integral from 0 to 1 minus x, because those are the values for x. And then we have the joint density, where now it'll be x plus z. Great. Now, so I asked you then to prove via the convolution formula that the density of z equals y minus x is a beta distribution, and find the parameters. So we let c be this constant, and then by the convolution formula we can take this integral and pull out things that don't involve x, and we substitute x equals the limits 0 and 1 minus z, and we get something whose variable part has the form z times 1 minus z to the 8th, which is a beta 2,9. Okay, so that's the class for today, and we'll continue on with convolution next time. Have a great day.